Yes, in Calcutta, it was very nicely conducted.
So everything is going fine with you?
Yeah, yes, sir. IIT Bombay is relatively, the number of cases have reduced. That's what we talk nowadays. Only number of
IIT Madras has increased.
that's what we are talking with Professor Robinson is the chair, and Dr. Rajesh Sachimurthy from IIT Kanpur is the co-chair. We were just talking about that only.
Good morning, Professor Mukherjee. Rajesh here from Kanpur.
Very good morning.
Manikant, Mani, Suhit Chakrabarti. Dr. Dipankana, who graduated in 2008, no, Rajesh?
Yes.
2008. Dipankana, you graduated in 2008, 18, no? 18 or 19?
Sir, 2018, end of 2018.
18 she graduated. Now she is with IIST, no? It is called?
Yes, sir, IIST Shipur.
Shipur. Oh, very nice.
Assistant professor, and she is doing very well actually.
Dipankana was our student at Jammu.
Yes, sir. They were actually both Dipankana and her husband were also my students. Very recently graduated.
Yes.
Yeah. And she got very good publications also, sir.
Yes, I know.
How is Robinson? How is Professor Rajgopal? Yesterday I have seen him. He was giving lecture actually for my lecture. Yeah.
So we are meeting very rarely that I am occupied with this admin work.
Yesterday, our what is his name? Arvindan was telling. Arvindan Nayak. What is his name? Anirudhan.
Okay.
Robinson has become very busy. I said,
you know better about this one.
You people have deal planning and chairman estate. For us, actually, it is combined. You know that. For everything, they'll say that the dean has to come and take decision. Sometimes small things also you will get very frightened, but it takes a lot. The presentation. And I said what has been constructed, what is being constructed, and what is going to be constructed. I presented. Then he said, so much of 400 to 600 crores of work, you are more like a builder, he said. And if you go to deal students, he will say, whatever your hostel you are giving, we are minus 4,000. That means that another 4 hostels are required. Another 4 hostels required means another 600 crores is required. And the CPWD is doing for you?
2 projects CPWD, rest we are executing. 400 crores we are executing, 350 crores. Remaining is by CPWD.
No, our all CPWD as of now, but CPWD also problem actually.
Yeah, they are also running short of
staff. 1.5 person will be there. You know, no? 1.5 person means that person will be there.
sharing with our place.
Sharing with other players. And tomorrow, if you don't see him for 2-3 meetings, then they'll say, sir, he has been transferred already.
Yeah, that happens.
Very ruthless.
Mm.
Yeah. I think time we have to watch. I think Rajesh 11:30.
Yes.
Yeah, 135.
And how many papers are there? Presentation.
As per
13
the
paper is listed.
Huh?
As
13
per the
papers.
schedule, it's 13 paper.
Okay. So what we do is that maybe I think on behalf of the organizers, I will actually start the session, and it gives immense pleasure to introduce Professor Robinson, my colleague in IIT Madras. In exact details of BTech and MTech, I don't know, but I know that he has done PhD from IIC Bangalore, and he has done excellent research work at IIC Bangalore. Then afterwards, he actually has done the postdoc at National University of Singapore. So where I happened to meet him and have long discussions. Then subsequently, I think after 1 or 2 years, within 1 or 2 years, I think Professor Robinson has decided to shift to India, and that was the good thing happened. As far as what I say is that IITs are concerned, any IIT, so with this, and at IIT Madras also, he's an excellent teacher as well as excellent experimentalist, and he actually has just now the co-chair that Rajesh was telling. We always look for Professor Robinson, which type of new setup he has developed, so that that will be helpful to the geotechnical community. So with this, please join me in welcome Professor Robinson to chair this session. So Professor Robinson. Now, yeah, and now I have the privilege of sorry.
So thank you for the introduction. Yeah, please go.
Yeah, I'm not read through any biodatas. Okay.
Because we know each other.
Yes. And we have Dr. Rajesh Sachimurthy, and one of our ex-students of IIT Bombay, and he actually has completed his PhD in 2010, and subsequently he did his postdoc from Grenoble, University of Joseph Fourier Grenoble, and one of the renowned university in France, where they have done excellent research on the landfill barriers. Then subsequently he joined IIT Kanpur, and now currently is associate professor, and where he has now developed what I understand is that unsaturated soil mechanics area, which is very much required as far as IITs are concerned, as IIT Kanpur is concerned, because very few faculties are working in that area. And yesterday, after going through Professor Sai's lecture, I was actually thinking about Dr. Rajesh, that Dr. Rajesh will have now many ideas wherein he can actually pursue these unsaturated soil mechanics, research, particularly, how this unsaturated soil mechanics concept can be brought into the course, wherein, this advantage of that advantage or disadvantage, we need to document that one. So, and couple of times, I think I heard that, he has also won the Best Teacher Awards in a short time. So that shows, his commitment to the teaching and research and all. So with this introduction, I would like to welcome Dr. Rajesh Sachimurthy to co-chair this session along with Professor Robinson. So in this, 13 papers are there, and I request co-chair and chair to take over and conduct the session. Thank you very much.
Thank you, sir.
Thank you, Professor Vishwanathan, for the kind introduction, introducing both me and the co-chair. I think you doesn't require any introduction to the audience. You are a well-known researcher in IIT Bombay, after your PhD from Germany, and so you are. I used to read through a lot of your papers on centrifuge modeling. Though modeling in IIT Madras because we don't have the facility, but some of the automations are very unique. Starting from Rajesh research work on the landfills. Then recently I reviewed one of your students' thesis on the compaction. They're all unique facilities, not easy. Those who work in the centrifuge,
Yes, yes.
and this is so glad that the three of us are conducting this session because all the three of us know what centrifuge is, the physical modeling. Yes. Just to start the session, the theme 9, numerical and physical modeling. This is one of the very, very important themes in any geotechnical engineering conference. Because geotechnical engineering is a practicing profession. But to do the practice, one has to design the structures. So if you want to design the structure, there are three components. The first component is the laboratory testing, element testing. One should get the soil parameters properly. Right? So then that soil parameters will be implemented or incorporated in the numerical modeling to make any design. But we want to, or we need to check whether the numerical modeling is appropriate. So to do that, one can carry out field tests, real full-scale field test, but that is not easy. It's very, very expensive and time-consuming. To complement the field testing data, so we go for physical modeling. So physical modeling in the earlier days, you do 1G test. In a laboratory scale, you do the test. But there are a lot of limitations, especially the scaling will be a problem. Scaling of stresses, the sulfate stresses become a big issue. So then the researchers invented this very interesting tool, the centrifuge. However, even now the 1G model tests are also very, very useful because they are much easier to do that. Now, this numerical and physical modeling, they complement each other. So we should appreciate the organizers for putting them together. They complement each other. So this brief introduction, let's move on to the paper presentations. We have 13 presentations as informed. I request Dr. Rajesh to take over and conduct the rest of the paper presentations. Dr. Rajesh.
Thank you so much, sir. Thank you so much. And so thanks, Professor Robinson, chairman of the session. Professor Vishwanathan, who is coordinating this session, and he is my teacher and guru. And I would like to thank Professor Satyanarayana Reddy also, the organizing chairman of IGC 2020, for giving me the opportunity to co-chair this wonderful session. So, with the brief introduction about the theme of the today's talk, this presentation, I think there are 13 papers right now, and as per the guidelines, the duration for each paper is 5 to 6 minutes, and so I have already seen some of the paper number. It's already written in chat box. Kindly, if you want to present your presentation, then kindly type your paper number in the chat box so that we know who will be presenting your work. Okay. So let's start with the first presentation. It will be done by Subhadeep, and then on the topic reliability analysis of settlement of foundation resting over a circular voids. So over to Kumar. So you'll be given 5 to 6 minutes.
Yes, sir. Is it visible, sir?
So you can share your screen.
Please share your screen. Present now, you press.
Yeah. Is it visible now, sir?
Now it is coming just. And Rajesh, you can also announce saying that try to avoid mobiles actually. accessing through mobile.
Okay. So the authors kindly keep a note of it. So still time is there, so you can go to the nearest place and then make it through laptop or the computer so that you can avoid using mobile. Because yesterday we have seen that we are unable to listen as well as we are unable to see the presentations properly. It is better to use laptop or desktop for better presentation.
Yeah.
So for other authors, kindly write your paper number in the chat so that we know the attendance as such. So over to Subham.
Okay, thank you, sir. Very warm good morning to.
Can you put a slideshow? Sorry, make it so that others can see.
Sir, I have put on slide only.
Okay.
A very warm good morning to all. I am Kumar Shubham, a research scholar from NIT Jamshedpur, and I am going to present my paper entitled Reliability Analysis of Settlement of a Foundation Resting Over a Circular Void. So coming to the my part, voids may occur due to the presence of tunnels, conduits, mining activities, and solution cavities in the bedrock. So, due to the presence and rapid urbanization and scarcity of land for construction, underground construction is becoming very much popular nowadays. But existence of such underground structure like voids may affect the structure in the vicinity. So, in most of the cases, voids formed after construction is not accounted for the design of foundation system. So this present study involves the determination of settlement of footing over void and its reliability analysis. At present, there are many research works going on, like determining the collapse load of footing, bearing capacity associated with the failure mechanism of footing resting over a void, and behavior of adjacent footings over a void, and many such studies are going on. So basically, we have redeveloped a model based on Betty and Wang. They have carried out a model footing test. So we have readapted that model and redeveloped in the Plexus. Load and position of voids. And for decreasing the complexity of the problem, we have used design of experiment concept for a two-level, three-factor full factorial design. And after obtaining various results from the studies using Plexus 2D, it is then processed in the Excel stat part, in which we have basically reassigned the values, like those parts which have failed, we have assigned it to 0, and those parts which were saved, we have assigned it as 1, and then carried out the reliability part. Coming to the results, for individual variations, like first we have the effect of vertical position of void. It can be seen from the graph that up to a variation from 0.5 to 1.75 meter, there was just a minimal increment, and after that there was a sudden jump in the graph. Secondly, if we talk about the eccentricity, that is the horizontal position of void, we have seen that after 1.75 meters there was a sudden increment in the settlement, and it was also not in the permissible limit. When we increase the load from 50 to 350 kilonewton per meter square, it was observed that the increase in the displacement was like what we have already presumed. So there was no sudden or difference from the pre-assumed literatures. When we talk about the reliability index and probability of failure, the reliability index was calculated to be 0.894, and failure of probability of failure was 0.185. And also the comeback alpha obtained was 0.965, which gives the consistency of data. The value of reliability index and the probability of failure shows hazardous condition if we consider the risk according to the settlement of foundation. Also coming to the regression equation part, a regression equation, that is a prediction of settlement, can be done through this equation, in which we can see if we talk about the interdependency or interrelations of the parameters, we can say that the eccentricity part does not play a vital role on settlement if we are talking about interdependence. Individually, it is affecting, but if we consider all the three parameters, it is not affecting that much. Now coming to the conclusion part, as the depth of center of tunnel increases from 0 to 3 meters, the surface settlement increases first and then decreases. It means the influence of tunnel location on ground settlement decreases as the depth of void is increasing up to a certain depth. That is the critical depth. It can be concluded that within a certain range of vertical location, the effect of depth of void is maximum. Actually, we are also working to determine the vertical critical zone. So that is not the part of this paper. Due to the increase in depth of void, the overburden pressure increases and simultaneously the value of axial forces, bending moment and shear force on tunnel lining also get increased. Third, there is no phenomena observed that demarcates the inverse effect of loading on the settlement. However, it has been observed that with the increase of horizontal distance from the center of foundation, the settlement decreases. And lastly, the reliability analysis became important as the solution for the presence of uncertainties in the result of failure of a structure using deterministic approach, because it is a complex procedure. Using form method, the reliability index for footing over single void is found to be 0.984 and the probability of failure was 0.185. So from USAC chart, it can be said that it was hazardous under standard conditions. These are the references. Thank you.
Thanks, Subham Kumar, for a nice presentation and sticking to your time. So we can have one question if anybody has. So maybe you can type it in the chat box, that is also fine. So if there are no questions, or if somebody has some questions, they can raise their hand. Otherwise, they can type the question in the chat box so that it can be done. Okay, so maybe we will move to the next speaker, Soman and Avadesh Kumar, on the topic behavior of buried pipelines in geosynthetic reinforced soil slopes. Soman is there?
Good morning, sir.
Good morning. Yeah. So you can share your screen and you will be given 5 plus 1, which means that it includes the question answer session.
Sir, is my screen full now?
Yes. Now it's visible. Yes.
Yes. Good morning, everyone. Myself, Somin Maskar from NIT Jamshedpur, and I'm going to present my paper on role of geosynthetics reinforcement in increasing the stability of buried pipes in soil slopes.
Soman, can you put
These are basically the contents.
full slideshow?
Yes, sir.
Slideshow? Can you put slideshow?
So now it is okay?
No, you press this right side button, slideshow.
Use slideshow.
1 minute.
F5.
So now it is okay?
Now it is good.
Yes, sir. So can I continue, sir? Yeah.
Please proceed.
Well, yes, sir. Good morning, everyone. I'm going to present my presentation on role of geosynthetics, reinforcement, and utility of buried pipes in soil slopes. Well, these are basically the contents of today's presentation. And I'd like to have a brief introduction of my topic. Well, buried pipes are used for numerous day-to-day works such as water supply, oil, natural gas, and electrical conduits, etc. During their course of laying, they have to travel larger distances, and at times they have to pass through severe adverse topographic conditions such as slopes, embankments, and others. At times, these slopes may fail due to various external forces such as earthquakes, landslides, heavy rainfall, due to which the failure of buried pipelines takes place within its vicinity. Thus, failure of pipelines located in slopes can be very catastrophic in nature due to structures lying above it gets collapsed due to relative soil pipe movement. Now coming to geosynthetic reinforcement. Geosynthetics are polymeric products and they are used basically as a reinforcing media to enhance the stiffness and strength of soil. The US Forest Services were the first to build roads for walls for roads in steep mountains during the year 1970s. These are basically the literature review. I went through various papers and based on that, I have arrived at my objective. What I have found is that although numerous researches have been carried out on buried pipelines located on level land, but very few researches have been carried out on buried pipelines located near the slopes. So based on that, I have carried out my modeling using numerical analysis and various influence of parameters such as slope angle, relative density, edge distance of footing, horizontal and vertical position of pipe on the behavior of footings have been carried out on this model. These are basically the pictorial representation of my modeling adopted, and these are the simulation steps used for modeling. I won't be going into the detail, but in a nutshell, I can say that features such as staged construction and various soil models present in Plaxis 3D enables the user to have a more closer and accurate simulation of various construction and excavation processes. Now, I'd like to continue with my results and discussions. At first, I have validated the numerical results with experimental work conducted by Lee and Manjunath during the year 2000. Well, from the graph, it can be seen that there is slight error, and this error might be possibly due to the error in simulating the soil properties reported in the literature. So, I have basically conducted my modeling in two phases. At first, I have considered the unreinforced slope, and next, I introduced GeoGrid in it, and I carried out my further analysis with a reinforced slope. So, in the beginning, at first, I have varied parameters such as slope angle, relative density, and edge distance of the footing. Now, coming to this. From the slide, it can be seen that slope angles 20 degree, 26.5 degree, and 30 degree have been considered in the analysis. And it has been seen that the load carrying capacity reduces with increase in slope angle. So the slope angle of 20 degree have been considered as the safest angle considered for analysis in this paper. Next, I have varied the relative density, and it can be seen that the load carrying capacity of the footing increases with increase in relative density. Therefore, relative density of 85% has been considered in this study. And last, I have varied the edge distances of the footing, and it has been seen that as we move away from the slope, the load carrying capacity of the footing increases. That means when the B by B value is 5, it is giving the maximum load carrying capacity. But to stay with the actual analysis of slope, we considered P by B is equal to 2 in this numerical analysis. Next, once the slope angle, relative density, and edge distance have been fixed, the pipe has been introduced in the model. At first, the pipe has been varied in the vertical direction.
Sorry to
And it has been seen
when
yes, sir.
So kindly go to the conclusion.
Yes, sir. Yes, sir. Yes, sir. Sir, when the pipe, it has been seen that when the pipe depth is d by b is equal to 3.5, it is giving the maximum value. Similarly, for horizontal variations, it has been seen that when the x by b value is equal to 2, the slope effect is negligible. Therefore, in case of unreinforced slope, the safest vertical and horizontal position is d by b is 3.5 and x by b is 2. Next, once the position of pipe has been fixed in case of unreinforced slope, geogrid has been introduced in the model. And based on that, again, the pipe has been varied vertically as well as horizontally. And it has been seen that when the depth of the pipe is d by b is equal to 3, the bearing capacity ratio is giving the same value in case of unreinforced slope, d by b is equal to 3.5. And next, the horizontal distance of the pipe has been fixed at 2.5 in case of reinforced slope. Therefore, in a conclusion, I can say that load carrying capacity of the footing can be improved with the inclusion of geosynthetics, and next, embedment depth of the pipe can be reduced with the help of geogrid. This will further help in reducing the trenching cost incurred during laying of these pipelines in soil slopes. And second, the pipes can be placed more closer to the vicinity of the slopes as the x by b value is increased in case of reinforced slope. And above all, geosynthetics in the form of geogrid is helpful in improving the overall stability of grid pipelines. Thank you. These are the references. Thank you.
Thank you, Shubham, for a nice presentation. It's a very interesting study. I think Spurti Rai is not
Thank you,
here.
sir.
So maybe we can move to paper number 45. And after paper number 45, there was a request. It will be paper number 50. So after 45, we will move to 50 because there is some request from paper number 50. So paper number 45 is Sweet Chakraborty and Amit Kumar Das will be presenting on time-dependent response of soft soils under tilted storage tanks. Sweet Chakraborty. Kindly share your screen and then you can start presenting.
Very good morning, everyone. My name is Shuhit Chakraborty. I shall be going to present the paper named Time Dependent Response of Soft Soil under Tilted Storage Tanks. With time constraints, I'm starting with an introduction. We all have heard about the storage tank and the importance of it in the industries. Construction of such storage tanks not only need proper design, but also we need to carry on regular maintenance. Such structures are often observed experience differential settlement after a certain time of operations. In the present study, we have performed a time-dependent analysis of soft soil under storage tanks to check for the tilting of such structures. These are the selected literatures related to the present studies. Were prepared and settlement profile of all the configurations is monitored starting from the loading stage to the 90% consolidation stage. Here the configuration 1 is having uniform depth of soil layer and rest all are having variation in the depth of soil layers. To validate the study, we have chosen a case study from Ramdan et al. 2013, it with present numerical model. We found the results are in good agreement. Results from the numerical analysis shows that there is both differentials as well as tilting in the storage tank structure in configuration 2, 3 and 4 respectively up to the loading stage, and it goes on increasing further with consolidation. Config has not suffered any tilting since it is uniform throughout. The result of time-dependent analysis of configuration 3 I have chosen here for representation, and since it has suffered maximum tilting of 23 mm up to the loading stage, after 90% consolidation, that tilting has crossed about 105 mm, which is almost 4.5 times the initial tilting after the application of surcharge. Going to the parameters, it is observed that with an increase in the undrained cohesion of the soft soil as well as an increase in the stiffness of the soil, tilting of the structure reduces. Tilting is a function of consolidation settlement which increases non-linearly with surcharge intensity and time. Tilting is observed to increase disproportionately with an increase in intensity because the rate of consolidation settlement increases with surcharge intensity but decreases with time. Next term, it is also observed that the change in the tilting of structure with time is almost linear for rafts of lower diameter, whereas the same is non-linear when the diameter of the raft is large. The conclusions, differential settlement may occur even in the foundation resting on uniform soft soil, but tilting is governed by the change in the thickness of the composite layer. Important point is that we have considered that tilting is the difference of settlement between the two opposite edges of the structure. Tilting of the surface with time as consolidation of the soil progress. With an increase in undrained cohesion of the soft soil as well as stiffness of the soil, tilting of the structure reduces. Third, the diameter of the storage tank, possibility of the tilting is higher. These are the references which I have gone through for the present study, and thank you.
Thanks, Sujit, for a nice presentation and sticking to your time. So it's an interesting study. So if you have some questions, we can post it.
I have one question. Am I audible?
Yes, sir. Yeah.
I have one question. I want to ask you that whether you have you have studied this consolidation parameters, and have you considered 3D consolidation, or you have gone with this traditional one-dimensional consolidation?
Sir, I have prepared 3D numerical model in Plaxis 3D for consolidation.
Plaxis 3D consolidation. And what do you consider? Drainage condition, is it lateral? Have you considered lateral confinement or this laterally?
Sir, I have considered lateral confinement as well as bottom is confined since rock layer, which is non-porous, and only the top layer is unconfined.
So basically, this is a one-dimensional consolidation condition.
Yes, you can see that.
But in Plaxis 3D, you have also considered this condition, no? As you told me that the laterally it is confined and bottom is confined.
Yes, sir.
Okay. Thank you.
Thanks, Dr. Arpan, for a good question. And let's move to the next paper. Paper number 50 by Dr. Arpan and Sujit Kumar on the topic analysis of 3 consolidation settlement of DeFi soil using Plaxis 3D under different drainage conditions. So over to Arpan.
Yes,
you can start presenting your work.
I hope I'm audible to everyone.
Yes.
Is my slide is visible, sir?
Yes, sir.
Yes.
Yeah. Good afternoon, respected dignitaries, chairman of this session, co-chairman of this session. Myself, Dr. Arpan Loshkar, and I'm assistant professor of Technical Engineering Agartala. Co-author is Professor Shujit Kumar Palsa, and he's professor at NIT Agartala. So this topic is quite related to my PhD, and this is a very vast topic, and I will try to conclude this within this 5 to 6 minutes. And the title of this topic is analysis of 3D consolidation settlement of C5 soil using plastics 3D under different drainage conditions. So this is the inspiration of my study. So inspiration is, as I told, that generally we ignore the lateral confinement of pore water during assessing the settlement. We generally ignore the lateral movement of soil particles. We generally consider the vertical movements of soil particles and vertical expulsion of pore water. And in practical, this conditions are not matching with practical condition, and generally we consider the anisotropic flow condition. That means we doesn't consider anisotropic flow condition. So these are some inspiration of my study, that we found that these conditions are not actually related to the actual field condition. So objective of this study is to develop a 3D consolidation apparatus where we can consider the lateral expulsion of pore water, and we can consider the lateral movement of soil particles, and we can assess the anisotropic flow condition. We can assess the settlement under different anisotropic flow condition. So it could be very much representative to the actual field condition. As you know, the consolidation is the expulsion of pore water from the saturated soil sample, and the assessment of this consolidation, the amount of consolidation and the time taken for the consolidation is very much important, other than failure will occur. This is an iconic example of a consolidation settlement failure. This is the Leaning Tower of Pisa. This is the traditional oedometer apparatus developed by Tarzaki in the year 1923, and this apparatus has different limitations. Like it has a lateral confinement, and it doesn't allow the lateral expulsion of water, and it doesn't allow the lateral movement of soil particles. And this one-dimensional condition could represent this condition. Here you can see this is the one-dimensional condition, actual field condition, where the loads are applying vertically and the sites are confining. And this is the one-dimensional condition, one-dimensional consolidation condition. And this is the three-dimensional consolidation condition, where there is no lateral confinement. Soil can move vertical in vertical direction as well as in lateral direction. Water can move vertical direction as well as through the lateral direction. So this condition, what I represented by the Tarzak in the 1923, this is not the actual 3D consolidation condition. This doesn't represent that actual field condition. So this table represents the error occur in one-dimensional consolidation. Here we can see there's a huge amount of error. So this is a 3D consolidation apparatus which I have developed in the laboratory of NIT Agartala. This is a 3D consolidation apparatus by which you can measure the 3D consolidation of any soil. So these are some materials I have used during my experiments. Coming to the comparison, before going to the comparison, I just want to show a load distribution method. I have considered this 2:1 load distribution method in case of 3D consolidation apparatus, and here you can see in case of one-dimensional consolidation, this is actual confined loading area. In case of one-dimensional consolidation, if my cursor is visible to everyone, this is the actual confined load area, and this dotted line showing the actual projection of a load. So this is a huge difference of one-dimensional load distribution and 3D load distribution. Coming to the comparison of compressibility, here you can see this is the compressibility of different soil assessed by one-dimensional oedometer and 3D consolidation. Here you can see the compressibility is high in case of one-dimensional audiometer up to 4 kg per centimeter square load, and beyond that it get decreased. And this is the coefficient of consolidation by 1D and 3D. Here you can see the coefficient of consolidation is higher in case of 3D consolidation test, because in case of 3D consolidation test we allow lateral expulsion of pore water and lateral movement of soil particles. That does not happen in one-dimensional consolidation. So that is why the coefficient of consolidation is higher in case of 3D consolidation. Coming to the 3D consolidation under anisotropic condition, anisotropic permeability condition.
Sarpan, sorry to interrupt. You have 1 minute left.
Okay, sir. Okay, sir. Okay, sir. So in 3D in anisotropic condition, here we have we may have different anisotropic conditions. So I have taken 5 different anisotropic conditions, and these are the different 5 conditions. And this is the graph showing that anisotropic condition doesn't have initial and final settlement, but it have a huge effect during the consolidation process. So this is the coefficient of consolidation graph versus effective stress, and it shows that case 1 showing the higher coefficient of consolidation. And if you relate this to this condition, one anisotropic condition, here you can see in case 1 have the all through lateral opening to flow the pore water. And in numerical analysis, I have gone through the Fluxus 3D, and this is Fluxus model showing the settlement under 200, 150 kilonewton per meter square, and this is the final. This is the result in final tabular form. Here you can see the deflection of a result between practical and the Fluxus 3D is kind of 4.73%. And in conclusion, I want to say that as one-dimensional consolidation have a huge error. So if we chose 3D consolidation in place of one-dimensional consolidation, it could represent the actual field condition in more better way. That's all. Thank you, sir.
Thank you, Arpan, for this presentation. See, I have a small comment. See, 1D consolidation has its own advantage. Okay, so, and it is meant for some other field situation, right? So it's for geostatic stress condition. So based on the field situation, you will have to use different test setup. Okay, and since the time is less, so if anybody has some questions, they can always post it in the chat box. So we will go to the next paper number 46. Thanks for it. Paper number 46, Smita Shivapriya Mukherjee and Gopinath Bandari on the topic effect of seepage barrier in steady seepage below earthen dam by scientific model. So over to Smita.
Good morning, sir.
So you can share your screen. So you will be given 6 minutes time.
One second. The screen has been shared, sir. Sir, my screen is visible.
No, not yet.
Not yet. One second, sir.
There is any problem in sharing?
Sir, yes.
So maybe can keep trying, and then we will move to the next paper, and then you can come back as a next presenter.
Okay, sir.
Okay. So let's move to the next paper, which is paper number 52 by Dipankana Bhattacharya. Yes. Dipankana Bhattacharya and Vishwanathan on the topic studies on centrifuge modeling of rainfall induced landslide.
So should I present my screen or
Yeah.
I think she's trying to present also. She was trying to interrupt, I think, sir. Will you just listen to her once? I think she has solved the problem. Should I present, sir? Should I continue?
Yeah, please you continue.
Okay. So with the permission of all, sir, let me share my screen.
Yeah. Please.
Sir, is the screen visible? Should I start?
Yes.
Okay. So a very good afternoon to all delegates present on the virtual dais. I am Dr. Dipankana Bhattacharya, Assistant Professor, IIEST Shibpur, and the topic of my discussion is Studies in Centrifuge Modeling of Rainfall-Induced Landslides. This is the layout of my presentation. Now coming to the research relevance, rainfall-induced instability of geotechnical soil structures is a serious global issue and deserves special attention. As far as the CRED database is concerned, which I have shown here, the frequency of hydrometeorological disasters is much higher globally as compared to corresponding geophysical disasters. Even as far as the national scenario is concerned, which I have summarized here, the estimated average losses in India due to rainfall-triggered landslide is about 550 crores a year, which brings out the relevance of the present study. The problem of this instability which I'm discussing aggravates if good quality permeable granular material is not available for backfilling. This eventually leads to the use of locally available low permeable soils or marginal soils as they are referred to as at the construction site. Hence, the aim of my present study here is to investigate the response of slopes constructed with marginal soil subjected to rainwater infiltration. As far as the modeling technique is concerned, centrifuge-based physical modeling has been selected in this study for understanding the actual physical phenomenon which is involved in this failure process. Now, what were the other options available to me? Full-scale modeling is time-consuming and difficult to replicate in case of a complex natural hazard like rainfall. And coming to small-scale physical modeling, it cannot predict the behavior of prototype slopes accurately owing to dissimilarities in stress levels and strain conditions between my 1G lab model and the prototype. Hence, what I have done is I have highlighted the stress and strain conditions here, the prototype model followed by the 1G lab model and the NG lab model. I have resorted to centrifuge-based physical model testing, wherein the model is subjected to a centrifugal acceleration having magnitude n times higher, as has been shown here, than that of the Earth's gravitational acceleration. The mechanism of rainfall-induced landslides have been investigated by monitoring quite a few aspects, namely the deformed slope profile, the slope face movements, the crest settlement, and the pore water pressure generation with rainfall. In order to extrapolate the model response to that of the prototype, we need to derive standard scaling laws linking the model behavior to the prototype. That is one of the basic fundamental requirements of NG-based physical modeling. Now, I'm not going into detailed derivation of how I derived the laws. Let me just briefly summarize the advantage of NG modeling, that the rainfall duration, as you can see here, the two representative graphs are shown here. The rainfall duration is reduced by n square times in centrifuge, whereas the intensity is increased by n times. Thus, the same rainfall is replicated once the prototype rainfall is replicated here, the duration being reduced and the intensity being enhanced. This enables simulation of long-term rainfall events in centrifuge. Coming to my model soil, as I already mentioned, the model soil has to represent the properties of locally available soils with fines present in major parts of India and other tropical countries. What I did was I blended sand and kaolin, locally available sand and commercially available kaolin, in the ratio of 4:1 in dry weight, so as to result in a soil with near about 20% of fines, as you can see, and a permeability of the tune of 10 to the power minus 6 meter per second. These are the various stages involved in model preparation. Briefly, let me say the instrumentation involved, as can be seen here, 4 Druck PDCR81 based pore pressure transducers placed above the compacted base layer, as has been shown here. With the help of a wooden formwork, as has been shown, the desired slope inclination was achieved. In this case, a slope inclination of 2 vertical is to 1 horizontal was maintained. Post-model preparation, a toe drain was also provided for draining away the excess runoff water. Here I have highlighted the results of 3 typical model tests performed. In all these cases, model T1, T3 as well as T4, this is the seepage tank. With the help of the seepage tank, an initial water table was maintained at the slope toe just at the onset of rainfall. And gradually how the phreatic levels changed with pore water pressure buildup was monitored with the help of the PPTs. As I have summarized, model T1 was subjected to a low intensity rainfall but a rather long duration lingering storm of 10 mm per hour. Model T3 represented a medium rainfall event of 20 mm per hour, very similar to the seasonal monsoon showers which we experience, whereas model T4 was an extreme climatic event, a very short and intense cloudburst of 50 mm per hour, which we can associate it, let's say, with the Uttarakhand floods that happened, global warming and associated climatic changes. And these thresholds I have chosen as per as the International Journal of Climatology, the database of LASA 2001, which specifies thresholds, which is a moderate rainfall, which is a heavy rainfall and all, as summarized here. This is the rainfall actuator which was developed for simulating rainfall in flight at high gravities. Due to time constraints, I'm not going into the detailed description of individual components. Let me just mention one important aspect, that is the nozzles. The nozzles here are specially designed air atomizing nozzles. As we can see, they have an interaction of pressurized air and pressurized water which can interact within the nozzle body and result in mist formation. Now, this mist formation is very important because it ensures identical impact pressure is experienced on the model ground as that of the prototype ground, and the slope failure which we are seeing is actually due to rainwater entering into the slope body and not due to extensive runoff based erosion. Adequate measures were also taken to ensure that we are able to control the intensity as well as the duration of rainfall in flight at any point of time during testing to replicate a diverse variety of natural hazards. And additionally, one of the major aspects in centrifuge is to counteract Coriolis. So we also, by various calibration tests, we ensured that Coriolis forces could be counteracted on the droplet trajectory and majority of the rainwater reached the model ground. This is the completed slope model, the model test package mounted on the swing basket, the details of the balanced beam centrifuge at IIT Bombay, and just one small GIF animation I have here. If rainfall is occurring on an unreinforced slope, how roughly the slope failure is happening. So we analyzed this with the help of image analysis. Let me go on to my results and discussion. This is the deformed slope profile which was obtained during post-test investigation with progressive rainfall. The first picture is that the model which is subjected to 10 mm per hour rainfall intensity. As we observed, a kind of a deep-seated phase failure was encountered in this case on account of deeper rainwater infiltration into the slope, and we observed multiple sliding stages in the first case. On the contrary, the second case, the model T3 subjected to 20 mm per hour rainfall underwent a very clear and distinct sliding failure about the toe near just about 15 minutes into model dimensions. The failure time in this case was about 15 minutes. And T4, which is subjected to a heavy torrent of 50 mm per hour, failed catastrophically and almost instantaneously within just about 6 minutes of rainfall due to extensive erosion. The failure in this case, let me say, resembled more or less of a mass block-based sliding. That's the slow failure pattern dependent on the ratio of the saturated soil permeability to the input rainfall flux. And the time which I have highlighted, I have monitored this up to a point of time when neither the pore water pressure transducers nor the slope movements, they did not change significantly with the progress of rainfall. So that is taken as the ultimate failure time up to which we had monitored. Neither the movements changed drastically, neither the pore water pressures changed drastically beyond that point of time. So that is regarded as the ultimate stage of centrifuge tests in all these cases here. As far as the other image analysis results are concerned, like the crest movements and the
Sorry
face
to
movements.
interrupt, Dipankana. So
Yes, sir.
maybe you will have to conclude soon.
Right,
Very
surely, sir. Surely, sir. As far as the crest settlements and phase movements are concerned, definitely all the 3 models failed, but the failure was more or less of a gradual kind for the first model as compared to the later 2. And the same here for the pore water pressure movements. For the model T1, we observed a very slow and steady rise in pore water pressure, where each stage of sliding corresponded to a stage of increase in pore pressure. So whatever I have discussed here, I have highlighted here. These are the research highlights, and I have tabulated my results here. Presently, we are working on how to mitigate this instability which is being observed and trying to work out whether drainage is governing or reinforcement is governing. We have developed a kind of an innovative hybrid geosynthetic. So that's an ongoing research. Thank you so much.
Thanks, Dipakana, for an excellent presentation and very nice work. So maybe due to the shortage of time, so if somebody has queries, they can always place it in chat box, and maybe Dipankana can answer it in chat box. So let's move to the next paper. Smita, are you ready now? Smita, paper number 46.
Sir, 1 second, sir. Yes, sir, my screen is here, na?
Yeah.
Yes.
Please proceed.
Thank you, sir. Good morning, respected professors, delegates, and participants. Today I am going to present my topic relating seepage and stability analysis of embankment using cutoff in the experimental modeling using centrifuge. The topic name is effect on seepage barrier in steady seepage below earth and dam by centrifuge modeling. This work done under supervision of Professor Shivapra Mukherjee and Dr. Gopinath Bhandari from Jadavpur University. This is the content of my presentation. All of you know that the stability of the river front embankment is very important aspects. Seepage plays an important role in the stability, and the most of the earthen dam failure due to the seepage action. Seed pile traditionally being used for support and protection of river bank. It plays an important role in the toe protection of earthen dam. With a seed pile, seepage can be effectively controlled and eliminate the risks of backward erosion in river front embankment. Seed pile cutoff also improve the stability of an embankment, lengthening the seepage line, enhance the safety with respect to the risks of hydraulic failure. Now, based on this motive, my objective of the previous study is to analyze the seepage behavior of the earthen dam and foundation using seed pile as in cutoff under steady seepage condition. To study the seepage analysis, my model of earthen dam is 17 meter wide and 4 meter height with twist to one slope. This is the model. And the variation of the seed pile length is V by 8, 5 meter length, 10 meter length, 15 meter and 20 meter length with different position like V by 8, 2 V by 8 and 3 V by 8 position. The output parameters that is studied, that is flow net pattern, fluid flow vector and factor of safety. In the present research, basically we use centrifuge technology to study the flow path using seed pile at seepage barrier. A series of tests have been performed to study the flow path, fluid flow vector and factor of safety. Basically, centrifuge modeling is a technique that's subjected to gravity force and to analyze the scale models from the prototype. The arm length of the centrifuge of Jadavpur University is 0.55 meter and the radius is corresponding radius is 1.1 meter. For geometric and stress similitude model dimensions are n times smaller than the equivalent prototype. The ratio of the area and is scaled as n square and volume likely n cube and time will be scaled as 1 by n square and seepage velocity like n will be scaled as n. The geotechnical centrifuge of Jadavpur University's Turner beam type carries a model at one end and counterweight at the other end, basically. The real-time water control of the water level is an important aspect, and this control system composed of control inlet and outlet valve and also sensor, IR sensor. The image data acquisition system has been controlled by RPI and also the connected with MATLAB and Wi-Fi connected. This is the step. This is some. This is some centrifuge modeling. This is the first one is the captured image and second one is the processed image. Flow net have been obtained from the vertical image velocity technique. From the process of the capturing of the successive image by sets of number of patches. The movement of the each patch traced by cross correlation function of PIV. Flows are interrogated manually and also by giving visualization of magnitude of the xy component of the velocity at different points and also at different times. Now coming back to the presentation of part, the ferritic surface using cutoff and without cutoff has been effectively studied by PIB technique. It has been observed that seed pile acts as a fluid barrier effectively. When seed pile shifted towards downstream end, average dimension of the last element of the flow line decreases. It observed that when seed pile length increases, seepage path automatically increases and reduces the exit gradient. It has been obtained that when seed pile length increases by 13% of the bottom wave of the dam, exit gradient decreases by 9.97%, and when seed piling increases by 59%, the bottom of the dam, exit gradient decreases by 18.16%. It also evaluated that if seed pile length increases by 30 to 59%, the bottom of the dam, exit gradient decrement also proportional to the seed pile length. Now coming back to the fluid flow vector. Fluid flow vector, all of you know that is discharge per unit area. In this figure, the negative signs indicates that the fluid flow in the downward direction. At the position of the seed pile, there is abrupt jump. When seed pile length increases, fluid flow is less, and decrease of fluid flow, it automatically in that case, when fluid flow actually decreases for 20-meter length, that is 30% less compared to the 5-meter length at any fixed position. Now this is stability part. Seed pile improves the stability by reducing the chances of hydraulic failure. Factor of safety decreases when seed pile position moves from downward direction. When seed pile moves toward downstream end, average flow length of the extreme field of flow net at downstream end increases, which reduces the exit gradient. Also, factor of safety against piping improves. As seed pile length increases, factor of safety against pipe also increases due to the reduction of the exit gradient. For any instant at B/8 position for 5-meter length, factor of safety against piping increases 20% compared to the 3B/8 position and 18% compared to the 2B/8 position.
This Smita, can you conclude? Your time is up.
Yes, sir. Now my conclusion is the seepage cutoff has been effectiveness of the seepage cutoff has been appropriately studied in the centrifuge-based modeling in the image-based analysis. Seed pile length when increases seepage path, which reduces the exit gradient in case of increase of seed pile length by 30% of the bottom width of the dam. Exit gradient decreases by 9.97%. Furthermore, when seed pile length increases 59% of the bottom width of the dam, exit gradient decreases by 18.16%. Exit gradient decreases by 8.17% if seed pile position is shifted from 14.25% of the bottom of the dam from the downstream end. For any fixed position of the seed pile, length increases when seepage path increases. Fluid flow vector decreases at seed pile moves towards downstream end, and its maximum for least length, and fluid flow vector reduces with increase of seed pile length that's studied through experimental modeling. Factor of safety against piping decreases by 18% when seed pile position moves away from the downstream end for a fixed seed pile length. As the seed pile length of the seed pile increases, factor of safety against piping also increases. Now this is my references.
Thanks, Smita, for a good presentation. Happy to see the results from small scale, the small centrifuge test. So I can take one question if anybody has. Okay, so there is no question, and if somebody has, they can type it in chat box. So the next paper is 53, paper number 53. Vaibhav is here.
Yes, sir, I am here.
Yes. So you can present your what? Topic is on studies on the performance of pipelines subjected to differential settlement, numerical study.
Hello.
Smita, please mute your mute from your side.
Hello.
Yeah,
Am I
Vishnu.
audible and my slides are viewable?
Yes. Please proceed.
Yeah. Okay. Thanks. Good afternoon, all of you, and thanks for giving chance to present my research work. This is on studies on performance of pipelines subjected to differential settlement. I am presenting a numerical part. This work is carried out under the guidance of Professor B.V.S. Vishwandam and Shantiram Chatterjee sir at IIT Bombay. So my presentation will have a brief introduction, literature review, modeling approach, and analytical finding for parametric study. So as we know that pipeline is one of the reliable, safe, and economical mode to transfer the life essential, and that's why it's sometimes referred as a lifeline for any developing nation. And since they are laid all over kilometers, so their exposures to the ground movement is unavoidable. And these relative motions between pipeline and the soil produce additional load on the pipeline. As per the EGIG report, this is the fourth major cause of pipeline failure. Now, if you look at this graph, the first three, which can be controlled with the help of better quality standards and corrosion management technique. But the fourth one, that is a relative, because of soil and pipeline related displacement, the loads acting, that need to be accounted at the design stage. And this is the pipeline failure over the period of time. And now we can see that the fourth part is becoming the critical. And this pipeline failure results in a great economical and environmental damage. So this is the pipeline failure from site location where a section got deformed and there is a fracture at the weld joint location. So before going for the research study, we have carried out the literature study in three domains. Firstly, analytical, centrifuge, and numerical. Now, in analytical domain, we found that Newmark and Hall had initiated this pioneering work where he had addressed the pipeline subjected to fault, and the formulation is developed considering pipeline as a cable, which was developed by Kennedy et al. For accounting the friction part, and that is considered in AISA standard, which is now becoming a standard guideline to design these kind of pipelines. So these models are further developed for accounting numerical and geometrical studies. And these model particularly customized for settlement study by Kutz et al. And Kutz et al. And there is one more approach which was developed by Wolstenhen or customized for settlement study based on Winkler Foundation. These models are limited because when pipeline having a higher D by T ratio, it's become a local buckling.
Socketed pipes of diameter 1D to 3D socketed conditions, depth of socketing. And we have considered 9 positions in the proximity of slope. The negative sign represents the piles on the slope, and the positive sign represents the piles on the embankment. So for this, we have used for the soil, we have used HS small strain model to model the soil, and in case of the rock, we have used a simple Moore-Coulomb model, and the embedded beam tool was used for the modelization of the pile, and medium mesh was used based on convergence study. Interface element was used to represent the friction between the soil and the pile. We have considered phase-wise loading to simulate field conditions, and boundary conditions used were these. So these are the properties related to the soil and the rock, and these are the properties related to the pile. And for the classification of the pile, we have used the IS 2911 code. And based on this, we can say that in all cases, the piles were classified into intermediate piles. So this is the typical mesh after failure. So for the validation, we have used ISO 1990 and AIC paper. So based on this, we have simulated the field condition in the in Praxis 3D using our models. And based on that, we have seen that the curves are in good agreement. So in our case, based on our study, that we have taken IS 14593 as the reference code, and the lateral load capacity of the pile was taken as the load corresponding to a lateral displacement of 4 mm. And we have also considered cases on a horizontal I'm sorry, undisturbed horizontal ground. This is taken as the ideal response. And for the zone of influence, if the lateral load capacity of a pile is reduced by more than 5%, this pile is considered to be within the zone of influence of the effect of slope. So considering this is the results and discussions, and the lateral load versus displacement graph for the unsocketed piles. Here we can see that the pile located on the extremity of embankment is the behavior is very parallel to the horizontal ground, and as the pile moves towards the crest of the slope and on the sloping ground, the lateral displacement is higher for lesser lateral load. So similar trend is observed in the socketed piles as well, although the values of lateral load capacity are significantly higher. This is the comparison of lateral load capacity. We can see that the lateral load capacity of the piles increases with the increase in the depth of socketing, irrespective of its position. So these are the discussions, the points we have discussed already. And we can also see from this figure that the rate of decrement of lateral loading is reduced when the depth of socketing is increased. So these are based on that. These are because the reduction of embedded depth happens when the piles position of the pile moves onto the slope, and this is because the resisting volume of the soil in the passive wedge is reduced, and therefore it is the piles on the slope are more dependent on the rock stratum to carry its lateral load. So we can see that in the pile on the extreme slope side is what is gaining most out of the effect of rock socketing, and it is improved by 42.05%. So this is the
Nandagopal, can you conclude its time now?
Yes, sir. 2 seconds. And this is the comparison of zone of influence, and we can see that from the unsocketed pile, which has a unsocketed zone of influence up to 12 times the pile diameter, it has reduced to between 6D and 3D in case of a 3D socketed pile. So based on this, we can say that the rock socketing is a very viable solution for the problem. So these are the conclusions which I have given. The increment of lateral load increases with the increase in the depth of socketing in respect of pile position, and the effect of rock socketing is more effective on piles situated on the crest and on the sloping ground as compared to the piles on embankment. The rate of decrement of lateral load capacity as the portion of the piles is moved from the embankment to the slope. Then the zone of influence due to the effect of slope decreases with increase in the depth of socketing. These are my conclusions. Thank you.
Thanks, Nandagopal, for a nice presentation and interesting study. I think there will be some questions definitely for this presentation. So maybe you can type it in the chat box and we will be answering.
Okay,
so
thank you.
Neeraj is here, he can present this one. Neeraj Kumar, paper number 54. Mr. Neeraj, you said you are okay with presenting next? I think yes, still I think the problem exists. Maybe we can move to the next speaker. Okay, so let's move to the next paper, paper number 56, numerical analysis of stability assessment of left bank rock slopes, Lavaram irrigation by Rajendra Kumar and Muthu Kumar.
Yes, sir. Yes, sir. Yes, sir. Can I share, sir?
Yeah, kindly.
Sir, my screen is visible, sir. Hello, sir. Sir.
Yes, it is visible now.
Okay, sir. Good afternoon, sir. So, my topic is numerical analysis on stability assessment of left bank rock slopes. My case study is a Polvaram project under the guidance of Muthu Kumar sir from NIT Tiruchi. So, this is my presentation outline: literature, introduction, literature, object of study, methodology, control analysis, conclusion, acknowledgements, reference. So, before going to topic introduction, now we are seeing number of landslides occurring in the because of the rainy season or any problems. The problem of slope failures occurs. So there are the types of failures may be natural and artificial rock slopes where there is a small, minor or local instability to occur. We start the degradation of the slopes due to natural weathering. For design the rock masses, it requires some decisions, judgments before to deal with the rock slopes. So the design of rock foundations includes two user analysis, bearing capacity as well as the sediment analysis and slippery analysis. Now, for the rock slopes, so there are two factors. One is controllable factors, other one is uncontrollable factors. In controllable factors, one is geometry of the excavation of the rock slopes, slope orientation, the slope angles and bumps. Other one is method of excavation of the rock slopes, that is mechanical excavation or blasting by bulk blasting or control blasting. Due to environmental also, vegetation, proximal engineering, you can control these parameters to not to fail the rock slopes. Then the other factors which not be our controllable things, those are the uncontrollable factors. First one is meteorology, the rainfall, we cannot control, temperature and freeze, the topography of the area, and the geology and geotechnics of the area based upon the rock properties, the giant present in the rock mass, stresses present in the rock, earthquakes. These are not able to control by human beings. So this is the literature survey. So I have done some study based upon this. I have done the analysis of the rock slope. This is my object of study. I have to investigate the properties of rock mass from this study and evaluate the rock slopes by using contour analysis by using FEM. Software is a phase 2 software. Then I have to design the support system for the slope stability. This is methodology. I have collected from material properties from the field data from the Polvaram Red Bank Irrigation Channel, and based upon the field data, I have done some laboratory testing. Then rock mass properties and inter properties from field as well as laboratory test. Then based upon the properties, I analyze the slope profile by using contour analysis using phase 2 software. For the case study, I have taken the Polvaram project. This is a small multi-purpose projects. It having two canals, right bank canal and left bank canal. The right bank tunnel is already over, so I moved to the left bank tunnel. Here the using for the two types of purpose. One is irrigation purpose, other one is for navigation purpose. So the dam is located in that area of the north is eastern Ghat range, having the main rocks are gneisses and charnokites, condolites are predominant. So this is the basic geology of the Polvaram site. It is having a stretch of 6 meters at the entry portal of the tunnel is slope is for slope. The entry of tunnel is portal rock is having gneiss. Then basic strikes of this area, and this is the structural discontinuities in the area, having the minor shears, having a slope of strike and dip is having 30 to 40 degrees. Strike is northeast east. Then some shears are present in the condylite formation, along with some strike joints, dip joints, oblique joints. So there are no folds and faults present in this area. This is the topographical map of the Polvaram site. This is the present excavation. So this is the profile of the my slope. These are some boreholes done by the government. So this is the profile used for my analysis of the rock slope analysis. This is the left bank approach channel. the site photos. This is the approach channel. Then this is the site photos. This is the I have used some material properties for the left bank collected from the field data. Based upon the Hook and Brown failure criteria, I used to estimate the based upon the composite strength of the rock, entire rock sample collected from the field, based upon the GSA value, argued values, and modulus, and disturbance factor taken from the literature. I have taken the one difference. One is the disturbance factor. Then collected some samples. I have done the Begelian test based upon the some values. ISRM correlation code. They are given the based upon the Begelian test. I find out the uniaxial compression strength of the rock. Then by collecting these properties, the GSA values, RQD, Young's modulus, all these values were imported in the rock lab software. From that rock lab, I find out the Hook and Brown criteria, MB, S, and A, and Morculum criteria, C and pi. These are the properties used for the analysis. One is the intact rock properties from the experiment of the laboratory. The rock mass properties collected from the field and collected from the rock lab software. So these are my analysis. In this analysis, I simulate the control model. But the control model is having some maximum ground displacements to capture movement of loose blocks. So in this, I have used the two effects. One is the without tunnel effect. Other one is with tunnel effect. This is the equation used for the FEM analysis, Morcom equation, and the Hook and Brown failure criteria. This is the control analysis. This is my slope profile taken from the map of the Polvoram site. So this is my I get the critical SRF value, strength reduction factor as 1.29. This is the displacement occur along the loose rock. Here, this is the boundary between the loose rock and the hard rock. From here, the failure will be occurring. These are the yielded elements. This is the based upon the curve versus strength reduction factor versus total displacement curve. Then I incorporate the tunnel effect in the same profile, control analysis profile. Based upon the tunnel excavation, there is some disturbance in the rock mass. So over the tunnel face, tunnel portal, having some problem in the loose rock, there's going to fail. Then my factor of safety reduces it to 0.8. So earlier it is 1.9. Then I model the rock bolts in the analysis. I've taken the length of the rock bolt is 10 meters. Then my factor of safety increases to 1.64 from 1.292 without tunnel effect, 0.864.
Rajendra Kumar, sorry to interrupt you. Kindly conclude.
Okay, sir. Okay, sir. These are my conclusions. So I have used the FEM control analysis by using the Morculum criteria as well as with the generalized Huckenberg criteria. In control analysis, the critical SRF is obtained is 1.29 without tunnel effect. With the tunnel, I am getting 0.8 effect. 0.8 is the SRF value. When I use the rock bolts of the length of 10 meters, end anchor at spacing of 1.5 meter, placing normal to the slope face, my factor safety increases to 1.64. This is a tank for the Polvoram officers and the Max Infra people to help me to collect the data from field. Thanks, sir. These are my references. Thank you, sir.
Thank you so much, Rajendra Kumar. Very nice work and very field relevant work. And if somebody has some questions, you can always write it in the chat box.
Okay, sir. Thank you, sir.
Thank you. So let's move to paper number 57 by Shrikar, Mittal, and then Sindhuja. The topic is on displacement-based analysis of retaining wall with narrow backfill under rotation about bottom mode. Shrikar is available. Yeah. Kindly share your screen.
Is it audible, sir?
Yeah. Share your screen.
Yeah, okay, sir. Sir?
Are you sharing it?
Yeah, just a minute, sir. I think. Just a minute, sir. Yeah. Sir, is it visible, sir? My screen?
Yes. Yeah.
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 Just a minute, sir. Is it visible, sir? Now, my presentation.
Yes. 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 Please
Yeah.
proceed.
Yeah. Uh, Yeah, first of all, I would like to thank everyone who has given me this opportunity to present my work in this big platform. Okay, today my presentation is a displacement-based analysis of retaining wall with narrow backfill under rotation about bottom mode. Myself, Srikar, Senior Research Fellow at IIT Roorkee, I'm working under guidance of Dr. Satyen Mitral, and my co-work, the colleague who shared my work is Sankarab Sindhuja. So these are the contents of my presentation: introduction, finite element modeling, validation of the model, whatever I have done in the finite element modeling,
Srikar, we are unable to hear you.
hill area, and over which a backfill over the backfill we see generally pavements and all those, and other such applications are like if we are constructing or widening any road, we'll be using such type of walls where the backfill width is conventionally very much less compared to that of uh, a normal retaining wall, where the backfill width will be very much less. So that's what my area of study is: retaining wall with narrow backfill, retaining structures built in front of stable rock face or a stable wall. Conventional earth pressures, in this case, what happens is conventional earth pressure theories like Coulomb's theory or Rankine's theory may not be applicable because they may overestimate the value, as the area of wedge participating in the failure may be much lesser than compared to that of conventional retaining wall. So in such cases, how to deal with the problem, that's what my area of study is. So generally, a retaining wall problem is dealt in three ways, as limit equilibrium analysis, displacement approach, and experimental approach. In limit equilibrium approach, we take a failure wedge where the area of the wedge may not be known, which can be obtained optimizing by the inclination of the failure plane. And coming to second approach, which is displacement based approach, where we are going to construct a model in any finite element package like PLAX, MIDAS, or any other FLAC or Abacus, and then we are going to see how the wall is going to perform, how the whole geotechnical structure is going to perform in the numerical model. And to experimental approach uh, is model type approach, where we can see visualize the practically the phenomenon or behavior of geotechnical structure in a reduced scale. So in this study, I have adopted a finite element model where I have considered a retaining wall. If you see on the screen, there is retaining wall with retaining wall represented by a plate material, and the blue colored material, which is nothing but the soil layers. And if you see the model, there are two constraints on vertical walls. What vertical boundaries have constrained in horizontal direction, as we need to avoid the soil from failure after application of design loads. And at the bottom, I have restrained in both horizontal and as well as vertical direction. And these are the properties, model properties. I have adopted more Coulomb model, most basic model which we are frequently using. Elastic modulus, I have taken as 30 MPa, poisson ratio is 0.3, cohesion is 1 kPa, has takes very small amount of cohesion of 1 kPa, as my study is totally related to sandy material, sand cohesionless soil. But this small amount of quantity will be helping me in numerically stabilizing the finite element numerical analysis. And coming to friction angle, I have taken around 29 and unit weight 13.4 kilonewton per meter cube. And normal stiffness of the plate material, which is nothing but retaining wall, I have taken around 1.26 into 10 raised power 7 kilonewton per meter, 4.2 into 10 power 5 kilonewton meter square per meter will be my friction stiffness. These values are obtained from the lecture study. So my present model. First, the take model is validated first. The present model is validated using a centrifuge model test, which was conducted by Take in 2020 2001. The major contribution of the Take is to study the effect of aspect ratio, which is nothing but width to the height of the retaining wall ratio on lateral earth pressure. Centrifuge model is simulated with a full scale model in practice in present study. Centrifuge model is accelerated with an acceleration of 35.7 g. So this is the model which was considered by Take in centrifuge model test, practical centrifuge model test. So if you see here, there is a compartment in this where we have a feasibility of reducing and increasing the width of the retaining or width of the backfill, thereby reading the earth pressure values. So finite element mesh, in my case, I have considered finite element mesh with varying widths. In first case, in bottom point, if you see, is about 184 mm, and second B is 75 mm, third case is 38 mm, and 15 mm is the last case, the most lesser aspect ratio, which is most narrower case in my present study. So these values, these widths are fixed according to the centrifuge test conducted by Take. So as it is my full scale, this 184 mm is going to represent a full scale width of about 6.57 meters, and 75 mm is going to represent about
Shikhar, sorry
2.67
to
and
interrupt.
1. Yeah, yeah, sir.
Yeah, you have 1 minute left. You
Yeah, sorry. Yeah, I'll be becoming. So this is the validation of my study. I've just compared the earth pressures for different widths I have considered in the study. It is observed that it is very well validated and considers the effects of arching and all those things in this study. So this is the as my study, I have given a rotation about bottom. So at the bottom I have given zero displacement, and at the top I have given a maximum of 0.4% of the wall height, which is about 20 mm. As the wall height is 5 meters, I have taken 0.4% of wall height into 5, which is nothing but 20 mm of displacement. So I have compared the quotient of earth pressure obtained from my finite element modeling and coulombs, and normalized it by this ratio. And it is obtained that as the aspect ratio on the x-axis decreases, this coefficient of earth pressure also decreases, as we see in the graph. So this is what my important assumption is. So if you see aspect ratio greater than 1, it is almost coulombs and K from finite element modeling and Coulomb are obtained to be same, and as it reduces, it also reduces. So these are the failure planes which I have obtained from this numerical analysis, which is strain distribution, maximum strain distribution. So if we see on the conventional retaining wall, we are getting a conventional failure plane. If you see most narrower retaining wall, as it is a finite element behavior is evident here, it is going to, this retaining walls are going to be resulting in multiple wedges. So I have compared, by seeing these results, I have compared my study with Greco et al. Of uh, theory analytical work, which is conducted by Greco et al.
Shikhar, kindly conclude.
Yes, sir. Concluding. So these are the three cases he has considered. So these are the failure planes I have obtained from finite element modeling and analytical method, which are almost same. So these are my conclusion. As width of the backfill decreases, lateral earth pressure acting on the wall reduces. Reduction in the width of the backfill results in multilinear failure plane. Conventional earth pressure theories result in uneconomical design for narrow backfill retaining walls. So proposed methodology can be adopted with precise validation of model and compare the obtained results with available limit equilibrium analysis. So thank you for giving this opportunity. Over to you, sir. Thank you.
Thanks, Shikhar. Thanks, Shikhar, for
Yes, sir.
a very nice study. And
Thank you, sir.
let's move to the next paper. This
Yes.
Srivastava is there. I have not seen her in the chat box. Paper number 58.
I think she was there actually.
Paper number 58.
She's in chat box, Rajesh.
Yes, sir, I am present, sir.
Can you?
Yeah, kindly present.
Yeah,
Share
should
your
I
screen.
present?
Yes.
Sir, is my screen visible?
Yes, yes. Please proceed.
So, good afternoon to one and all. On the onset, I want to thank the dignitaries and the organizing committee of IGC for allowing me to present my research work on theoretical simulation of experimental results with Barron's theory for consolidation of soft clay by radial flow using PVD. My guide is Dr. A.V. Shroff, Professor Emeritus, MS University, Vadodara. The rapid development and associated urbanization have compelled engineers to construct earth structures, including major highways, over soft clay deposits of low bearing capacity coupled with excessive settlement characteristics. So amongst various ground improvement techniques, vertical drains is one of the oldest and most widely used technique to pre-consolidate and strengthen weak compressible soils. This technique decreases the drainage path of dissipation of pore pressure dissipation, thereby allowing faster consolidation, reducing time schedule, which can make cost-effective project. So the theoretical background considered over here is of three-dimensional consolidation given by Tarzaghi. Various researchers have worked with respect to various theories. The theory of Sandrin was given by Randulic 1935, Barron 1948, and later Richard 1959 summarized the theory. So we have considered free strain and equal strain condition, and Tarzaghi's three-dimensional equation condition was split into two parts, that is radial flow and vertical flow. And considering the radial drainage and applying the boundary conditions, we can obtain the degree of consolidation by Barron's equation for UR is equal to 1 minus E raised to minus 8 TBR upon F of N. And the value of TBR and F of N, how are obtained, are explained in the successive slides. So basically, the theoretical time factor used in Barron's theory is calculated. The row type odometer is used for the present investigation with 254 mm diameter, and the value of the drain is 25.4 mm. So the N value is obtained by the ratio of radius of odometer to radius of drain, which comes out to be 10. So by taking the function f of n equation from Barron's theory, we can get the, substituting the value of n is 10, we can get the value of f of n is 1.578. So the equation given by Barron for degree of consolidation is UR is equal to 1 minus E raised to minus 8 TR upon F of N. So if we substitute the value of UR as 10, 20, 30 up to 100% degree of consolidation, we can get the value of TBR. I've taken one example over here where we are substituting the UR as 50 and finding out the value of TBR as 0.137, which is also depicted in this particular graph of degree of consolidation versus TBR. So basically, the experimental setup that we have adopted is of MS University, Vadodara, which is row type hydraulically pressurized odometer with modified arrangements of measuring pore pressure at 3 radial points by Bishop pore water setup and settlement by dial gauge. So we can see over here that the hydraulic pressure system is used to apply uniform distributed load to the soil cake. So the hydraulic pressure system has got two dashpots, and under the principle of manometer, difference in manometer, the hydraulic pressure is applied on the convoluted rubber jacket in the row type odometer. The convoluted rubber jacket is placed in between the top plate of odometer and the middle ring, in which there is a pre-consolidated soil cake, and the bottom plate has got three pore pressure measurement radial points at an angle of 120 degree to each other, and they are connected to the Bishop's pore water pressure measurement system. The top plate has got a central vertical stud on which the dial gauge is fit, so that when under the application of hydraulic pressure, there is the settlement as well as simultaneously dissipation of pore water pressure taking place, and thus we can measure the settlement in the dial gauge and the pore pressure at 3 radial points with the help of Bishop's pore pressure system. This is a schematic diagram of a row type odometer, which shows the top plate, the middle ring, and the bottom plate. The bottom plate has got the 3 radial points where the Bishop's pore pressure measurement is connected. The middle ring has got a consolidated cake, and a central vertical drain is provided over here. So under the hydraulic pressure, there is a radial flow taking place, which comes into the PVD or the prefabricated vertical central drain, and thus the water is collected into the vertical, into the trough, as shown in this particular figure. Then basically the properties and the material used in the present investigation. So we have used 4 types of drains, that is sand wrapped with Boltzmann filter paper, sawdust wrapped with Boltzmann filter paper, sawdust wrapped with geotextile, and jute wrapped with polyamide polyester geosynthetic. And the soil used in the present investigation is a kaolinite with liquid limit 59.6, plastic limit 33.3, percentage plasticity index 26.27, and soil classification is CH with coefficient of permeability as 0.6 into 10 to the power minus 6 centimeter per second. We have performed the dehydration test for identification of mineral of kaolinite using muffle furnace, and the assay curve shows or interprets that kaolinite mineral is present. Along with that, we have performed liquid limit hydrometer analysis and dry density versus moisture content test for the kaolinite soil. The soil sample is prepared with double the liquid limit and is pre-consolidated.
Sorry to interrupt, you have 1 minute left.
Okay, so basically I'll directly come to the results and discussion. So as already explained earlier, we have calculated the theoretical time factor for using variance equation. Similarly, we can find out the experimental time factor and using variance equation. So by substituting the values of UR, we are getting the TVR theoretical and experimental for various degree of consolidation. And we can see over here that a graph is plotted for theoretical and experimental TVR value versus degree of consolidation. And it is observed that up to 20% degree of consolidation, there is slight variation observed. And after 92% degree of consolidation, there is slight variation observed. And there is a very good fitting in between 20% to 92% degree of consolidation. This is for the sawdust circular drain for N value of 10 at pressure 80 kPa. The variation initially observed is because of the hydrodynamic lag in the pore water pressure dissipation, and later it is because of the secondary compression effect, that is resistance to depression of the absorbed water. Similarly, we have plotted for the different drain materials like sand drain, the JPPG drain, and for the sawdust wick, and we can see that for the jute wrapped with polyamide polyester geo drain, the fitting is very well with the theoretical and experimental values as compared to other 3 drain materials. Thus, I will conclude that for all drain materials, the 6% initial variation and 6 to 10% variation at the end of primary consolidation in theoretical and experimental curve plotted for degree of consolidation and theoretical experimental time factor is observed. JPPG curve fits well compared to other drains. Initial variation is due to hydrodynamic lag in consolidation, while end portion variation is because of secondary compression of soil due to depression of adsorbed water in clay water system. I wish to acknowledge my thanks to my management, my guide, my guru, Dr. A.V. Shroff, and one and all who are indirectly and directly connected in this work, my references, and thank you.
Thank you, Ruchi, for a good presentation. Let's give a chance to Shruti Roy, if she is around. Paper number 42. Shruti Roy is there? Yeah, kindly present. You can present your work.
Good afternoon.
topic is on parametric study of stone column using Access 2D by Shruti Roy and
Yes, sir.
Adesh Kumar Chinna.
Sir, am I audible?
Yes.
Hello. Yes, sir.
Yeah, you are
Can
audible.
you see my screen?
Yes.
Okay. Okay. Thank you, sir. Good afternoon to one and all. My name is Shruti Roy. I've done my MTech in Geotechnical Engineering from NIT Jamshedpur, and today my topic is numerical analysis of stone column using Praxis Studio. So these are the various contents that we are going to cover today. Here, like introduction. Coming to introduction, as we have constraint of time, we'll be doing it fast. We are in the introduction. So, in my research, major interest has been confined to the soft soil, usually considered as the most problematic soil due to inadequacy of bearing capacity, due to inadequate stiffness drainage, and due to the settlement problems. Now, these reasons lead to the use of ground improvement technique. Now, when we come to the soft soil, the stone column is assumed to be the best way to treat soft soil. Actually, it uses three mechanisms known as reinforcement, densification, and consolidation to improve the soil. Now, coming to the objective, uh, here in my research object, my objective was to study the influence of various parameters like shear strength, area replacement ratio, etc., on settlement and deformational behavior of stone column. Now, coming to the methodology, like model preparation, here in methodology, I have used numerical analysis that has been done using finite element method software, Praxis. So here in model preparation, here this is a kind of schematic diagram used by Nasir et al. I have actually modeled that the model used in laboratory experiment by Nasir et al. Has been simulated by me here using Praxis 2D, and then a load settlement curve was observed. Now, coming to these were the material properties used in the model. And after this, for the purpose of validation, load settlement curve of the Nasir, and that was observed by me in Praxis were compared, and that was observed to be in the same site, kind of similar. Hence, after the successful validation, further modeling was done, and around 7 parameters were observed by me, and out of them, few of them I'm mentioning here, which has very visible result. And these are the parameters: the undrained shear strength of the surrounding soil, area replacement ratio of the stone column, slenderness ratio, and loading area condition. So see, since stone column is not binded by any binding material, hence we can only make it effective by keeping balanced use of parameters that plays important role in its effectiveness. Coming to the influence of shear strength of soft soil. To study the shear strength of soft soil, I have varied the values from 30 kilopascal to 40 kilopascal to 50 kilopascal, and effects were observed. From numerical analysis, it was observed that this was the graph that I have observed. Now see, here we can see that as we increases the shear strength of the surrounding soil, load bearing capacity of the stone column is also increasing. The reason behind this could be like when shear strength of surrounding soil is increasing, at that time, the passive resistance offered by the to the column from surrounding soil also increases. Hence, that makes stone column stiffer and also reduces the radial bulging, and hence we get the more bearing capacity. This was the discussion that I observed from there. Now, coming to the another parameter, that was area replacement ratio. So, the area replacement ratio is basically percent area of the soil replaced with the column. Now, here area replacement ratio was doubled from 0.38% to 1.52%, and this was done by increasing the diameter of the stone column. And here it was observed that load bearing capacity was also increasing with significant margin when we were increasing this area replacement ratio. Here is this is the value we can see here, 1.78% when it was 30 kilopascal, but 40 kilopascal and 50 kilopascal. So here this may be, here you can also see with this graph. This is given that this is witnessing that observation. Now see, when load bearing capacity was increasing, I guess that is due to the mechanism that it's called densification. That is due to the when we increased diameter of the stone column, densification increased, and that led to the lesser radial bulging and more transfer of axial load to the base, and that's why I think we got that increased bearing capacity. Now moving to another parameter, and this is cleanliness ratio of the column. Yes, cleanliness ratio bringing LYT ratio, and this was done by changing only length of column and not diameter of column here in my lab. So what I did, I changed that ratio from 3, 4, 5, 6, and what I observed that this was the effect on load settlement curve, but the main very important parameter, stress concentration ratio, was seen increasing very rapidly from the value LYT ratio 4 to 5 value. So I think this is the it will be always more optimum and economical to keep the LYT ratio between 4 to 5. And from the previous studies also this has been witnessed, which I observed here. And now coming to the loading area condition. Influence of loading area condition, in that case, there would have been two conditions, like when only column was loaded and the entire area was loaded. So keeping in mind the equal strain theory, that we assume that both the column and soil will be always intact, that we assume. And keeping that in mind, we conducted this, and what we found here can be witnessed here. See, in load settlement curve, we observed that when only a column was being loaded, at that time settlement was higher as compared to when entire area was loaded. Now this was due to the equal strain theory, which itself is a vast topic, so we're not going into that. So other than that, also I have assumed so many parameters that, but for them results were not that much beneficial. What we observe that with increase in artificial strength of the surrounding soil, with increase in the area replacement ratio, and with increase in the and keeping that LYT ratio between 4 to 5, and also by changing loading condition, load bearing capacity can be increased with a significant margin. We have to just make a balance between these parameters to get a more effective stone column construction. And these are the references. Thank you. I'll wrap up my presentation. Thank you.
Thank you, Shruti, for nice presentation. And if somebody has a query, then they can type it in chat box. So let's give a last chance to Neeraj, if he can present his part.
Sir, can you hear me now?
Yes, yes.
I hope you can see my screen now.
Yes, yes.
Firstly, extremely sorry for the inconvenience from my end, and thanks for bearing with the technical glitch. And coming to the topic, I'm Neeraj Kumar. I did my master's from IIT Bombay. I'll be presenting upon the effect of EPS diaphragm on the lateral earth pressure reduction, in this case in a retaining wall, and it's a numerical parametric study. So coming to the contents, these are the contents for the current presentation. And getting into the introduction, as we all know, the retaining wall is a structure that holds the soil at a slope greater than its natural slope. And these days, the retaining walls are of various heights, like ranging from 2 meters to 10 meters and above are used. And as the retaining wall height increases, we know that the lateral earth pressures coming on these walls also increases. And for the higher lateral earth pressure will result in the large cross-sectional dimensions, which makes the structure huge and uneconomical. So there are various earth pressure techniques which are employed to reduce these earth pressures coming to the retaining wall. And use of the EPS geoform as a comparable inclusion is one such technique. So several researchers have carried out experimental and both numerical studies in this area, and I have listed few significant works in this area. And in all these areas, the interface properties of various material interfaces in the system are not accurately captured or considered. And EPS geoform in all these cases is modeled as a linear elastic material, and where in the current study we try to model it with an orthogonal model. Coming to the objectives of the current study, the significant objective of the study is to model a retaining wall with a geoform inclusion, and also to validate the model, and then to carry out a parametric study to understand the influence of wall height, inclusion thickness, and the inclusion stiffness on the extent of lateral earth pressure reduction. Coming to the experimental work has been carried out to obtain all the material parameters that are required as an input for the numerical modeling. And I have listed the tests that have been carried out. And for the shortage of time, I'm not getting into details. And coming to the numerical work, once we obtained the required material parameters from the experimental work, we went on to proceed to the numerical modeling. So Plaxis 2D software, which is a finite element software, has been used in the current study. So the following work has been done: the development of the numerical model to simulate the EPS geoform compressible inclusion, and then to validate the numerical model that has been developed, and finally to carry out the parametric study. And in coming to the parametric study, we have chosen 5 wall heights, 4 different EPS geoform densities, and 5 different inclusion thicknesses as a part of the study. And as a backfill material, we have used NOR sand, which is standard grade 2 sand, and plane strain analysis has been adapted in analyzing the retaining wall. So table 1 shows the mechanical properties of the geoform, different types of densities of geoform that has been used, and the table 2 shows the values of the different parameters that has been adapted for the parametric study. And the table 3, which shows the parameters obtained for various materials and interfaces from both the experimental work done earlier as well as some of the other previous works. After getting the required material parameters and input for the numerical model, we went on to develop a numerical model, and as shown in the figure 7. 7 shows the geometry of the numerical model representing a retaining wall of height 6 meters and with an inclusion, which is a geoform inclusion of thickness 0.2 h, which is 1.2 meters. And the figure 8 shows the boundary conditions that has been adapted in the current study. And figure 9, you can see the details of the soil, the geoform, and the retaining wall system. And once the numerical model has been developed, we have validated it with the small-scale physical model from Ethical and Randolph in 2011. So once the model is validated and we got a proper validation, we went on to proceed with carrying the numerical simulations. So in total, we have carried out 100 numerical simulations, and to compare the effect of these various parameters, we have calculated the total earth force per unit length of the retaining wall, the isolation efficiency, and the maximum earth force. The total earth force per unit length has been calculated using the equation 1. The isolation efficiency, that gives the efficiency by which the earth pressure has been reduced by the compressible condition, has been calculated using the equation 2. So coming to the results, as you can see in the figures 11 and 12, the figure 11 shows the variation in the lateral earth pressure profile on the retaining wall. In this case, the EPS geoform stiffness has been varied, whereas the height of the retaining wall as well as the thickness of the geoform inclusion has been maintained constant. And coming to the figure 12, in this case, we varied the thickness, whereas the height of the retaining wall as well as the stiffness of the retaining wall has maintained constant. Coming to the observations and conclusion, so from the validation of the result, we have found that the LSL has been made to the model which has been used in the current study for modeling EPS geoform can be easily identified by the compressible inclusion. And the numerical parametric study has reveals that the use of the compressible inclusions can lead to significant reduction in the earth thrust that is coming upon the retaining wall. And specifically the geoform stiffness, which directly correlates with the density and its relative thickness, plays a predominant role in the extent of this lateral earth pressure in the retaining wall. From the figure 10, you can see that the lower portion of the retaining wall, there is lateral deflection, so which allows the soil to move in the opposite direction, resulting in the runoff of the soil and thus reduction of the lateral earth pressure in the lower half of the retaining wall. And it also has been noted that the thickness of the inclusion, with the increase in the thickness of geoform inclusion, there has been increase in the lateral earth pressure profile along the retaining wall, and also with the increase in the stiffness of the geoform, there has been an increase in the lateral earth pressures. So the isolation efficiency has to be as observed to improve with the increase in the relative thickness of EPS geoform inclusion, given the stiffness is maintained constant. So the maximum isolation efficiency of 46.6% was observed for 6 meter high retaining wall with EPS 15 geoform inclusion of thickness 0.25 h, in which case it is 1.5 meter thickness of the EPS geoform. So when it comes to the height of the retaining wall, the isolation efficiency improved with increasing the height of the retaining wall up to 6 meters, and beyond 6 meters, when the height of the wall is increased, the isolation efficiency of the system has kept reducing. Thank you. these are the references.
Okay, good.
And,
yeah, fine. Thank you, Neeraj, for a very good work. And
thank you.
so thank you all. I think we are coming to the conclusion or the end of the session. So over to Chairman, sir, Professor Robinson.
Yeah. So it's a very nice theme dealing with numerical and physical modeling. So we had a very good session. So it is a little, we took a little more time, but it's worth listening. So we had 13 presentations, which deals with a variety of topics, starting from settlement of foundation, buried pipelines, stone columns. Then we have consolidation. We have a classic problem of seepage below depth dam by centrifuge modeling. So then again, centrifuge modeling of rain-induced landslides. Then we had problem on earth pressure reduction by various means, on rock socketing of laterally loaded piles. And then we have one problem on slopes, radial consolidation, etc. So we had a variety of topics, both from experimental side, then numerical analysis. We also had a paper on reliability analysis, etc. So we had a nice flavor of all the topics. I believe that all of us had a good time. And so unfortunately, this is the COVID time. We could not have a physical conference. Nevertheless, the presentations all went on very well. So I take this opportunity to thank all the presenters for making effort and made a good presentation. So though 1 minute, 2 minute, we took more time, it doesn't matter. So we enjoyed all your presentations. I also take this opportunity to thank the organizers for giving this opportunity to share the session. Now over to Professor Vishwanathan.
So thank you, Professor Robinson and Professor Rajesh, for conducting the session. And I could see that, yes, you know, in the numerical and physical modeling, people are actually attempting to solve the problems by using, you know, the Plaxis-based methods, and you know, they are actually able to present. That is very interesting development. And we also seen one paper on the centrifuge modeling. So there's a first attempt actually, which they have done. It's very nice. And so with that, you know, the session actually, maybe I think 10-15 minutes is below time, but you know, this is could be expected because of the network issues and several other problems actually. Maybe the presenters also facing problems, or sometimes we are also facing. So in view of that, I think this session is, you know, very interesting, and also given us some new ideas, particularly restrained backfills. I think I've seen many people are attempting, and which is, I think, very much required as far as you know, the developments in the hilly areas is concerned. Okay, so on behalf of the organizing committee of you know, the IGC 2020, and the on behalf of the organizing chair, Professor Sachinarayan Reddy, I would like to thank you know, Professor Robinson and Professor Rajesh Satyamurthy for conducting today's session. And yesterday, Professor Chandan Ghosh and Professor Rajesh also had actually about 12 to 15 papers they conducted. So in total, we actually have got a good flavor of all the papers. And to the best of my knowledge, I think this could be the one of the longest session, and this is the one which actually what I can say theme, where you know, more number of papers are there. So that could be one of the reasons. And I also seen that the presenters are able to present very well. Today is much better. Yesterday, though we had one or two problems, but today I think everyone have done a good job. So I think the participants actually over is there, and they get the applause, and also the chair and co-chair and yesterday's chairman also are thanked. So please join in thanking them in a big way. So I request others, particularly Shruti Roy and Ruchi Srivastava, Rajendra Kumar, Dr. Dipankana Bhattacharji, and Professor Shupri Mukherjee to kindly sign off. So we need to discuss for 5 minutes about some other aspects organizing committee has put on our responsibility. Thank you. Thank you. Thank you, Manikant. Thank you, Anil Chiryanji. Anil Chiryanji is very active in both the sessions. Actually, he has given a number of suggestions to the young researchers.
Yes, yeah.
Yeah, thank you.